Thank you. You can hear me. I can hear myself, so I guess you can also hear me. Welcome to our talk. So it's a bit cybersecurity and machine learning, and what we're talking about is anomaly detection, which is a bit a peculiar part of machine learning, because what you're looking for, you don't know what it is and how it looks like. So or we can formulate it, you don't even know it exists. What are we going to do today? I will very quickly introduce ourselves. Then Alex will take over for the technical part, and he will state the problem, show how we solved it, show the challenges that we encountered. So, as promised, first short introduction of ourselves. We are from Ergon Informatik. Ergon is a software engineering company here in Zurich. It's almost 40 years old, and we have a lot of university students that come to work for us later, many also from the ETH. We have 3 locations in the Seefeld, and now the most recent addition is an office in Frankfurt in Germany. At the bottom there, you can have a laser pointer. You can see that we won the Swiss Arbeitgeber Award last year. So it's always good to work for the best Arbeitgeber. Just saying. The cybersecurity division of Ergon is called Airlock. This exists for about 20 years, and our products are securing web applications mainly in Switzerland, but also in growing number of other countries. And there's just a very brief overview of our products. I know you're not here to buy cybersecurity products, but it gives you a little bit of context what we're talking about. There's 2 main products. One is the identity and access management, which is basically authentication to web applications, which includes also like administration, self-services, onboarding, etc. And then there's the Airlock Gateway, which is a web application firewall, first and foremost. It protects against DOS attacks or bots, or it does very clever filtering, finds all kind of injection attempts and so on, any kind of dubious attempts. And this is where the Anomaly Shield is. Since a few years, we have this Anomaly Shield, which is a machine learning service that tries to detect just sessions that are weird, that don't look like other web sessions. Alex will detail much more about this. Very briefly about ourselves. I'm Adrian. I work for Ergon for almost 10 years. And I work in the identity and access management part that you saw before, the blue part. But last winter, I had the opportunity to work on this machine learning project together with Alex. That was a lot of fun. And now Alex will take over and introduce himself first.
So thanks. I just pushed the mouse out of the picture. It kind of grows bigger the more I look into it. Okay, so about myself. You see me here riding to the work after Zurich cancelled Bahnlinie 15. Most important part, currently I'm a student here, bachelor student, so I'm one of you. And I had a life before, but doesn't matter. I'm a working student, so basically doing a bit of earning money beside of ETH. And let's just jump into what's kind of the problem, why is it problematic, and so on and so forth. And it's already kind of obvious, anomaly. We don't know exactly what it is, but we don't want it. And just a simple example, like we look into the data our clients provide to us. We see something like normal session. So let's assume a client from Liechtenstein, he logs into his online banking app, and everything seems fine, so nothing too particular of interest. And then we actually see an interleaving session. Basically, the same online bank application, the same bank account, but now it's from Singapore. And it's not just switched from, let's say, Liechtenstein to Singapore, so somebody just kicked in his VPN, but actually it's interleaving, so back and forth. And now you have like the idea is like the session being hijacked. Did somebody kind of steal credentials? And now he's trying to get money from the Liechtenstein account. Now you're in the decision problem like, would you like to terminate the session or not? Or is it like a legit session where grandma tries to buy some presents for her grandkids and for whatever reason is from Singapore? So who would say, let's terminate it? The hackers are getting out of hand. Nobody would. Okay, some of you would. Who would say, okay, grandma, take your chance, buy whatever you would like for your kids? Okay, all of you are undecisive. Okay, well, here the story was actually, we cried wolf falsely. So basically, it was a legit client. He was in Singapore, and then we found out if you're on your mobile data, the mobile carrier in Liechtenstein still had the Liechtenstein IP, and if you just tries to connect to a wireless in Singapore, then you get a Singapore IP. And if the wireless is not of particular quality and you just drop back to a mobile carrier, then you see this kind of pattern. So basically, we kind of shut out somebody who should not be shut out, but that's how you learn from it. And the different decision problem, like it continues, legit session. So when we talk about session, it's like every time you make a click with your mouse, basically you send a request, so dozens of requests, depending on the website. And normally nobody searches through everything. I mean, imagine you go to eth.ch, nobody go through all of the links. You just go to whatever is of your interest. So the search pattern is a bit of like this. And then suddenly you see something like this, so somebody is really, really fond of the website and tries to search all of the links. Now the point is like, okay, I assume nobody searched manually. Nobody had like 5 hours of clicking around following each link. And now the part of the problem is like, is it some kind of a new bot, new crawler bot? For example, after Huawei got kicked from Google, they decided to build up something new and similar. Is it maybe like a reconnaissance or preparation for attack where people try to figure out where actually could you insert your drop table statement? Maybe somebody just making his kind of hobby project and try to index ETH himself or herself. Or for example, you see like a lot of dead links. So 404, page not found, and you see just page not found, 20 of them. Yeah, I mean, somebody might have had like, bookmarks. All of them are dead. Happens, but I mean, it's not that common. And also what makes life also hard, it's just not like, it's already hard to decide what's actually anomalous and what's anomalous and maybe also bad, but it's also the data we have. So if you just have a normal project, or Kaggle data set, it most likely looks something like this. So you have normal behavior in the majority group, and then you have malicious behavior, which is kind of like 30 to 70 or 60-40, whatever. But when we look at our data, that's how it looks like. Then we zoom in, and maybe we find one attack. And the problem is not that people are just really surfing in high quality way. We have a lot of rogue requests, so somebody tries to drop tables all the time, but there are already like security mechanisms in place, and it's just like we don't want to recreate what's already there, so we have to kind of think of actually sessions, so a lot of different ways to attack, and there are quite few, so there are quite few successful attacks, so it's hard to just learn on them and just say, okay, let's go for some supervised learning approach. So you have to resort to unsupervised learning and go for anomaly detection with the idea in mind, what's actually an anomaly, and is it like, if you type in your password 5 times wrong because maybe you came from a party and you're hangover, is it like anomaly or not? Maybe. Is it like malicious? Maybe not. And ways to tackle it. So right now I already said, it's kind of hard, but you cannot just cry and do nothing. So how do you tackle it? So that's like a basic slide. We just show you that it kind of starts with, okay, we have already an existing product, and Adrian said it exists for like quite a few times, so you just cannot just say, okay, I dump my Python Jupyter notebook somewhere, deal with it. You have to think how to include it, and nobody wants to wait until Python processed all of the requests. You have to make it asynchronous. After you have an idea how to integrate in the product, you go and say, okay, basic idea what somebody learned in ITML or ML or whatever, the subjects you see here with machine learning in it. And basically like, okay, now I know how to get data, how to incorporate in the product, but at the end it's always way complicated. And I mean, you don't have to read through all the slides. It's basically just saying that, it's a bit of work attached to it, and we use a lot of data and different types of models. And I'm gonna jump into the model themselves. I assume they are of more of an interest if we are talking about machine learning in anomaly detection. And I just start with model classes. we don't just use one model. We actually kind of map the model classes to what we would like to achieve. And yeah, let's start with the simplest ones, so clustering. The idea kind of comes handy like, okay, we have a group who surfs normally, and you have like normal users, you have users who surf in Chrome, users who surf in Safari, whatever. But then you always have like some kind of people who don't belong anywhere, and the idea would be to say, okay, I assume they're just not normal, they're the outliers. And we try to do it like on a lot of different attributes. You see like HTTP status codes, past timings. We use isolation for it, so when I came in 1 year ago, I was like, hey, why don't we use just one meta model and let's decide what's good, what's bad. We use some SVMs, especially on the outliers in the status code, so a bit of more exotic stuff. And then for the easygoing parts, we also use some kind of just statistical models. And now you're like, okay, and we got promised like state of the art and whatever, but I've already seen this everything in the lecture, so it should be like a bit of more complicated. We actually have something which we don't use in production, and we'll also jump into it, why not? But we also use some kind of recurrent neural nets and also self-organizing maps to see how they could help us or why shouldn't they help us. And let's just have like a short look into why sometimes it's hard to have a good model and then just to decide not to use it. So here is one of the most simpler models in the string sequences. So with path, I mean, like the URL which you're typing it. Or each time you click on the link, you go to a different path. And they come in a sequence. Obviously, if you surf for like 10 minutes, you have 10 minutes of data. And the basic idea is like most of you, if you visit a page, maybe more than once, but also if you just read the page once, you have an idea where you would like to actually navigate. So it comes with, let's not say predefined, but a highly likely sequence. And what we've done is basically built up a relatively moderate network with some recurrent elements of it and long short-term memory, and just put the data with the sequences into it and look whether we can predict actually like how high the probability of the next path of the URL coming up. And the idea would be if you surf in a very likely way, it's most likely that you surf like everybody else. And if you surf in a very unlikely way, maybe it's not exactly what you should be doing. You see here we're a bit of underfitting. You see that the training was a bit lower than the validation, the accuracy of it. But once again, it's just like the first approach. And here what works well, what works not so well. So basically, both of these sessions are garbage. I mean, you see someone tries to find the admin and the lead PHP and whatever not. Obviously, we don't have this one in our application. At least I am not sure whether we have them. And somebody here tries to just go and find a WordPress exploit. And when you look at the scores, here we're like basically 0, and here we are basically nearly 1. And what happens here is what we find out, there are like hundreds and thousands of exactly this type of exploits. So people who just use some kind of automated bots to just try to basically brute force one of the different ways to attack the application. They always use exactly this one in a sequence, and now the idea of if people follow a sequence like other people, then it's good. And if people follow the sequence, which is not so common, it's not that good, it kind of breaks down. Because once again, everybody trying to attack our web page brought this in this sequence, and then a predefined sequence, and basically it not works that well. But after finding out that the initial idea is not that easy to push into like the way we had in mind, we actually found out, okay, actually it's a bit of a problem more with data modeling. So what we come to restraints, what kind of constraints we have is it has to run on the client's machine. So it's not like we provide a service for the clients and then it runs on our hardware, but basically it should run on the hardware of the clients. And then it comes to like space, memory constraints. And for this one, we kind of decided that, okay, we needed to store a lot of data just for this particular model, and we were not sure whether the clients would actually be okay with it or not. So it kind of worked. So predicting of probabilities worked well. I mean, yeah, once again, even if it's not what we liked, but it actually detected the sequences pretty likely, but we couldn't put into the production. One of the other topics like SOMs, which looked pretty great in the paper, and I mean, you look into a self-organizing map paper, you see like a hexadiagonal maps, and then it looks everything great. So like neurons firing up and finding themselves what's good, what's not. We tried it. We just made a simple 24 by 24 map. You see some of the neurons never fired. And yeah, the blue, the dominant color, is actually everything is normal. Everything with a color was where we know that they triggered some of the mechanism we had before. You see actually that they kind of group themselves together, but there's a lot of mixed things going on. So now the laser pointer doesn't work, but basically you see each time when you have not a blue group, you always have something on the boundary, and the boundary is actually where we would like to know whether it's a good session or a bad session. That's where the decision is actually hard. And when we looked into it, it was actually not that easy to judge just from the SOM. So we kind of had to refer to other models, and we just find out how they do it in academia. They just write, hey, if we find a cluster where their sessions are labeled as malicious crawler, so they also used web browser data, then they just say, yeah, that's our intelligent crawlers who can kind of behave like humans. So it sounds pretty neat. So it's academically a pretty nice idea. But basically what it says, like, yeah, well, we kind of misclassified, or the self-organizing map misclassified. And we just say they behave like humans, and we put them in a human cluster. But we cannot do actually to the client. I mean, you cannot say, hey, you got hacked, but it was very elegant crawler, and it was very elegant attack, and it hacked you, so deal with it. So we said, okay, we had to refer to something which a bit more rigorous in the approach. And yeah, for example, like sometimes you have to refer to a bit simpler stuff, the isolation forest. Like, I mean, if you are not familiar with the model, so basically it's a tree-based model, and it tries to isolate, it's in the name, each sample and the features and the metrics you throw into it. So basic idea, if you have to isolate me from all of you, and then you would say my glorious hairstyle is already isolation enough, then with one feature it's already like done. But if it's like, and that's how it works in the data we use, like if you kind of isolate it through the amount of, let's say, requests processed, nobody serves for 50K requests. I mean, if you serve, you maybe serve maybe 100 or 200 clicks. Nobody serves with 50K, I would assume. Basically, what you see there is how the anomaly plots and the scores look like. And the more exponential it looks like, the better it is. But reality is often disappointing, so it's a bit of rough. And as already stated in the name, we did some non-automated feature selection. And the problem is, when you come to the point what kind of features to bring into it, then from the lectures you know, okay, I can either use everything, then it just runs for like an eternity, and then you're still not sure whether it was good or not. You can kind of do some kind of PCA, so dimensionality reductions, which we also tried. Then the problem is now you know that the principal component number 5 is important. So what exactly is principal component number 5? And at some point it was like, okay, we have different models. I will just drop a few informations where I use different models at the end. And we try to don't correlate the features within different models, because otherwise you're kind of predicting everything the same. We try to use features which are not correlated here. I mean, the algorithm itself would do pretty well with correlated data, but it's not nice from the statistical point of view. And what we also done, we just use a lot of sharp to kind of make an explanation what actually goes on. And it's model agnostic, so we don't have to refer to the feature importance from the tree itself. And by then it was a bit of like iterative process. You ask people who actually know way more about cybersecurity than I do, like, do you think that, for example, specific timings are important or not important? And at some point it was like, okay, we have a good idea what works, what doesn't work. We put into the model and hope for the best that actually completes or helps the other models. And one word or 2 sentences why we actually use different models. Once again, different parameters may be anomalous, but for each one of them you can find a use case, as with the session in the beginning, whether somebody just changes his IP address and it's not VPN, which might work and it's like a legit session. But if you have different models and different sets of features and all of them go like red, you cannot argue that, yeah, okay, it's still a grandma, but she clicks like ultra fast, and she also like just look into the HTMLs and she completely ignores CSS files and whatnot. And that's why we decided to have several models and all of them produce an anomalous score. If you're anomalous for all of the models, then we say, okay, let's stop this session. It's getting out of hand. And now the main point is, you can basically use any algorithm you want. At some point, somebody asks you, how good is it? And it's already hard to define what we are looking for. It's also kind of hard to find in the data. And then it's like, is it kind of impossible to say how good our models are and what should be done? And once again, in the university on Kaggle, you just get a description like, this is an anomaly. It has a 1 or a 0 in the CSV. Nobody tells me what to do. So what you have to do is manual labor. And if you're in a research group, then you basically find a Ph.D. or research assistant who basically does the manual labor. If you're a company, you find a working student who does it. And unfortunately, I'm the working student, so I have to do it. So you go and look through the database of IP. It's like one of the easiest way to find it. You go to look through the paths where the people are trying to brute force your backups and your Docker files, whatever not. You have to gather a lot of data, obviously, but it's not that obvious where you get it because not all the data which are publicly available have exactly the same structure which our product actually generates and uses. And you cannot map one-to-one. So we gather data from our own sites, and that's also where we test and see how good it runs. And at some point, you kind of have to come to the conclusion that just manual work will not cut it. People can attack a website way faster than I can actually see whether it's an attack or not. So what we've done is basically we've written some kind of predefined rules where we say, okay, that's obviously good, that's obviously bad, and use it on the data we gathered. And it's obviously the results are as good as the rules are. It does not scale to everything because otherwise we just use the rules. But it kind of helps to see whether everything else which is not rules defined still find the session or not. And we deal with something like last time it was 250K sessions when we look into them. And here we have just a fragment of them and also just a fragment are anomalous. But it's better than nothing. It's still better than just, manual labor. We have, by the end, I said multiple models. Some of them perform pretty well. Some of them perform not good, but we just at some point said, okay, we can kick them out in the next version of the product. And that's how it goes. One of the aspects which are kind of always dropped when you look into the tutorials, when you look in the projects, and which I was a bit of shocked how much work it actually is, it's like fighting for the performance. And I will present you a classic Greek tragedy. Classic tragedy has always 3 acts, and we start with the first. And after committing all the models, running the checks and seeing, okay, we have nice performance, the next week you kind of find a Jira issue. And first act is just sad. It said impaired performance, like it's my baby, now you called it impaired. And then you see that they actually classified this a bug because it was slower than the version before, and it's bad. And the final act is you see in the components and who is assigned to, and you're the guy doing machine learning, so you can blame others. It's the tragedy as it's defined. So you kind of have to deal with it, and there's no way around it. Otherwise, we will not ship the product you kind of worked for the last half a year on it. And there are a few ways how to actually fight for the milliseconds. And it's libraries, it's actually vectorization, or the prediction pipeline, and also reading the docs. And let's go through a journey back and forth with the libraries. So I did not found nothing. I found actually like a working code. It was already incorporated. It was just starting where somebody else left. And it was written in pandas because it's convenient. But pandas is definitely not the fastest library to deal with any kind of numeric computations. So we switched to NumPy. It was not that convenient, but we got nice speed up. Some functions were way faster. Not just 4 times, but once again, we have a lot of strings. If you have a country in it, country like CHDE, whatever, it's already a string. You could kind of hash it, but whatever. You have paths, which are kind of hard to just hash numerically. And by the end of the day, we get a speed up. It was not as good as for some functions, but was okay. The next idea was, okay, if we use NumPy and it's great, how about Numba? And we decided, so we looked into it, and it was sometimes extremely fast, like 100 times faster, but at the end of the day, it was not that faster than NumPy, like 5 times speed up compared to 4 times speed up. And the idea is, or why it did not work that well, is just it has way too much string computations going on. And then we said, okay, we just benchmark the models, which of the models are actually slow. And we found out it was isolation forest. And while it's fast in training, the predictions were going like each time was the most computer costly operation to actually go through the tree and find the prediction. And what we come to is Treelight, and it's a pretty nice package. You can basically push any kind of tree-based models into it. Then it compiles for 3 hours or something into millions lines of C code. And you open it up and it just says if value below blah, 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 and like 3 million times. And then it runs like hellish fast. Like, I mean, 670 speed up. It's not like I forgot a decimal point or whatever. It was like extremely fast. And then I actually proposed to use this one. And the answer was, yeah, but it actually runs on a component which is attacked by the internet, and we need a C compiler on it. So if anybody breaches the component, so our security way, and find a C compiler, then you're actually done for good. So while it was a nice speed up, we had to kind of push the idea back and say, okay, we resort to NumPy, and if we need the speed up even more, we will find a way to do it differently. The differently was pipelining. So basically, that's, I assume, what a lot of people just already tell in lectures. And if you see the tutorial, it's kind of obvious, but once again, out of convenience, you say, oh, we have a data structure in Redis, so basically a database. And it just goes like you pull some sessions, you have an ID, by the ID you get the next one, you kind of process them one by one. And that's what's actually implemented. And you already see it's like not the most efficient idea if you think about it. So you can kind of just pull the aggregates, and then you have a vector of data you would like to predict, and then you push it to the prediction engine. And that's exactly how sklearn works. So if you just have a live stream of data, and we work with live stream of data, it's a moderate speed up just because there are a lot of other applications or operations which are going on, not just the prediction engine. But if you have to analyze data in a batch, it's like nearly 500 times the efficiency. And that's actually what kind of made the difference between we have to analyze data from our client and then you start it overnight and hope the next day it's ready to, okay, you started, then you go drinking a coffee and then you come back and you have to work. And the last one, reading the docs, I mean, it's kind of a meme, but sometimes it helps. So after checking in NumPy, checking in the batch predictions, batch aggregations, whatever not, the decision was, okay, let's go and update it to sklearn 1.0. because it's promised a faster learn in the k-means clustering. And then it goes like this. So basically, it used 16 cores instead of 2 on the production machine, and it was 3 times slower. So the first thing you do is you Google how to delete commit from history, because nobody should know what you failed. Actually, when I presented the slide in a dry run to my boss, and he was like, this really happened? I was like, maybe. But then you actually go to the docs, and what happened actually, sklearn just said, okay, the njobs parameter from sklearn, from the clustering algorithm is deprecated, and now the MP Open library should manage it. And for random reasons, it just uses all of the cores if it's not specified in precise way, which is not inside the model, and we use everything inside the model. So we kind of found it out on the second day, but it was like 2 days of painfully going to work knowing that there are some issues and you are responsible for them. And just a short summary. We compare here a bit like what I've seen in the university and what it actually looks in our way. It's first of all the objective. Here, if you do a project or you do a Kaggle competition, it's always stated exactly what goes on, what you should do. For us, it's just not obvious, and also the big drawback is you are the one being asked. So you don't have your peers, you don't have a professor to ask, it's you. With the evaluations, once again, like you don't have a public leaderboard where if you're number 1, then you're done. But you basically have to start with manual work. And at some point, it's also like, if you don't detect anything, is your model just great and you haven't been attacked? If your model just garbage? So it's a bit of a philosophical question. I said, yes, stay pessimistic. And once again, you have to push yourself a bit. At some point, you come to a conclusion, okay, what we worked is actually working good. So you have some marketing slides which are saying, okay, we find everything within the first 10 clicks. But once again, did you find enough to make this statement? And yeah, it's still like sometimes a lot of work and manual labor and so on. And also the runtime. Once again, I was kind of dazzled by the amount of work you have to put in this optimization. Especially, maybe the main message is training. Nobody cares for it in training in our work because, if you say to the client, okay, you train it for 2 days, he'll say, yeah, it's a great algorithm. It has to train for 2 days. If you train it for 3 days, you'll think it's like 3 times as efficient. Oh, sorry. But the actual runtime of the evaluation, what's actually the trick for us. And this is also, you see like a second tragedy going on. Then you have really specific questions and there's like no real help. So yeah, that's how actually my search in Stack Overflow looks like why nobody answers me. Then you push a question and you still get a lot of people looking into it, but like 0 answers to it. And that's all from my side. And we have some time for Q&A.
So yeah, if you have any questions, just raise your hand and we'll get to you.
You mentioned a few challenges and sad parts about working. What are your favorite parts working on this?
So one of the favorite parts, so I would say 2 parts were pretty nice. So one of them was like having on one monitor the research paper somebody done, and then their own work and see why it's not working the same way, because then you can either see whether it works well or not. One example was we had a research paper from brain activity, and they described that neurons fire either very regularly or in bulks or random, and they transfer it to how the requests come over time. And you can imagine that a bot will most likely be very fast and very regular, but a normal person will either have bulks, so he clicks somewhere, and then he is AFK reading, or being really random. And you see this, you transfer it to your data, and then it suddenly either works or not. And it was pretty cool because then you can transfer the research knowledge. And also, if you see how your optimization actually speed up, and then you see the first time like hard data, like it runs from, let's say, 150 milliseconds to 10 milliseconds, then you can say, it's a speed of X, because once again, it's a small island of certainty in a sea of uncertainty around. What's your favorite part, Adrian? No favorite parts, just pain.
I think what I like the most is when you create a model like the RNNs, the path analysis of the network, and you just throw in all the sessions, and then you look at when you look at the results, you can very quickly see if it makes sense or not, and that's kind of I thought that was a cool experience when you see that what comes out makes sense, or sometimes it just completely doesn't. You cannot explain why it comes out, but when it's explainable, it's always fun.
Anybody else? Because I have one marketing slide and I will show it for like 7 minutes.
Yeah.
How did you use RNN specifically? Did you get embeddings of that come out from the model and then you feed it to another model like a multi-layer conception?
Yes, the paths were embedded just to make it more efficient. And then the basic idea is it learns the sequences, like it knows which path comes after the next, depending on the previous paths. And so it always has probability. So it's not the prediction that we care for, but the probability distribution. So if you have seen this, and this path, you have a probability distribution for the next one. And so if the next request then is actually a likely path, it gives a high score. And if it's a low probability, it looks bad. And then if that continues, I think we average the probabilities, and if it continues to have low probability requests, then it looks suspicious.
And then would it make sense to use transformers instead, since they can learn longer sequences, or in this scenario?
It might. We just didn't follow up. It was not efficient enough, and especially memory-wise. For the training data, we condense it very much to like a database of like 50 numeric values per session, and to have the training data for the RNNs, we would have to store the whole path sequence for each session, and that's just exponentially more memory, and just we didn't follow it up.
And also, just as add-on, our problem was already like you have some predefined sequences which works very well, but which are malicious sequences. So just having like a better sequence detection or better probability of sequences would not work. So we had to work around. And with the memory constraints, we decided not to put more effort into it.
Are you continuing to train the model with like data you get from customers, or is it all sort of done and dusted?
Okay, so how it works here is, so we get our data like on weekly basis, and we have also innovation clients who are looking into like what new features do we have, and they provide us data, but not on so regular basis. So sometimes you get a chunk of data for like 1 month, and it's great. And sometimes you get like maybe 3 days, and then it's like how much statistic can you do on 3 days? What's interesting is when you get like a successful attack from a client, then we get the data to analyze. And that's also where we kind of have some of the very few points where we can test the models against the attack, like did it work, did it not work.
Also, I'm not sure in which direction your question went, but every customer, like every web application that is protected with this, first goes through a training phase. So the models are trained on a specific web application and then applied there.
Okay, then as I said, marketing made me do it. We have a stand 1 floor below. You can get some goodies out of it, and especially popcorn. That's what I'm interested in. Go for it, and thanks for your time.
Yeah, and there's just to say, there's also contests. You can win very cool prizes. I mean, I think it's really cool prizes actually. You just don't have to do much for it, but you have to participate and maybe talk to us. We will also be there for a while longer if you have more questions. Thank you.
Thanks.